Thank you very much for the introduction. Hello, everyone. I'm David, and today I'm going to talk about, maybe I want to enumerate the title again. Basically, the model for time series forecasting with non-Gaussian distribution applied to the machine condition prognosis. So moving on, and also this is joint work with Dr. Ireneusz Jabłoński, Professor Radosław Zimos, and Agnieszka Wołońska. Yeah, so the outline of this presentation is, first of all, our stated problem, which also points to the presentation that Professor Wołońska has said. Then I will go through our proposed solution with aspects that contribute to the architecture of the model, applied distribution, loss function that is used for training of the model, and upside task, which is important part of the loss function. Then I will move on to the evaluation of the model. So first of all, comparing it with the model that is based on Gaussian distribution without any proposed enhancements within the model. And I will evaluate the model on simulated and real data. So starting off from the problem statement, as Professor Wołońska said, the goal is to estimate how the health indices will perform in the future, so that we can estimate the remaining useful lifetime of a machine, so that we can predict when we should actually repair it, so that there are no many obstacles within the production pipeline. So with this we want to estimate the probability for the when a given threshold will be reached, so that we can estimate the road, so remaining useful lifetime. So the challenges within this problem are that the data are highly skewed, non-stationary. There are many outliers, so the distribution is overall heavy tail. And also for the forecast, we don't want to predict only a few samples in the future. We want to do a long-term prediction. So our proposed solution is to use deep learning framework, for which we will predict the parameters of the distribution. So the assumption within this model is that the whole dependence given the data is embedded within the parameters of the distribution. So this is pretty much stated in this very short equation. So given the trajectory from T1 to the length of this trajectory, we will get the vector of parameters to T plus tau, where tau is the number of samples that we want to predict into the future. So moving on to the components of the proposed architecture. So for this model, we propose to use a very flexible distribution. So the skewed generalized T distribution, which is a generalization of the student T distribution, defined by the probability density function. This is very important for this model, because for that we can use the log likelihood optimization, which is very easy to do within the deep learning framework. So this is defined by this. The PDF is defined with this equation, and with those parameters. However, when we apply those parameters, we sort of assume that a first and second moment exists. So if we want to drop this assumption, we just set the m and b values to 0 and 1 respectively, and then the parameters mu and sigma won't be representative of the location, maybe the first moment and the standard deviation of the distribution. So the interpretation of the parameter change a little bit. So the parameters are as follows: the mu, which is location parameter, sigma scale parameter, and the additional parameters, so the lambda, which contributes to the skewness of the distribution, and p and q to the cortices, or just the general heavy tailness of the distribution. So moving on to the tree, so we see that this distribution is indeed very flexible, because it contains many well-known distributions. So, for example, Cauchy distribution, Laplace uniform, of course, student T distribution, and also Gaussian distribution. And with that, because maybe those P and Q parameters are not very easy to understand, so we can just say that within the student T distribution, P times Q is the same as the number of degrees of freedom. So the the product of those two parameters, the smaller then the distribution is more heavy-tailed. So with the proposed architecture, I will go through each component of this architecture. So starting on from the input vector. It is very important to first pre-produce the data so that we can actually efficiently train the neural network and extract the features without any problems with the gradient, and so that the learning procedure won't cause any problems. So in the first row of the tensor, we have the sample that is standardized. So because we deal with non-stationary data, we have outliers. So first of all, we use robust statistics for location and scale. So basically, those are conditional means and standard deviation. So there are conditions on the quantiles of the data. Second point is that we don't standardize whole vector of the time series. So we standardize based on first few samples. So in our approach, we propose using 200 first samples, so that the beginning of the time series is located at 0 and has standard deviation around, the scale is around 1. It is because of the LSTM that I am using in the later stage. I will also talk about it, which within this layer we assume that the beginning is somewhat alike because we start from certain assumptions. So this will help the model to overall produce better results and don't produce any non-linearities within the, or maybe discontinuities within the prediction. The second row within this tensor is the embedding, indicating whether the sample is provided. So one indicates whether the value indicates the true value of the trajectory or not. And so you can see that the tensor doesn't contain only like the samples of the trajectory, it also contains zeros. So the zeros indicate the values that we actually want to predict and forecast. This allows us to efficiently estimate and actually forecast the distribution, because as we would have to go through every sample in the time, this isn't feasible, because when we predict the distribution, so that we need to sample from the distribution, and with every single step we need to sample from the distribution and samples, and so on and so on. So we have the exponential complexity with the ability to predict n samples, tau samples. This complexity is diminished very much. So okay, so the input is described, and moving on to how this is produced. So we take the copy of the input and move it to two twin layers, maybe blocks. So the causal CNN block, so the convolutional block, contributes to extracting features from the trajectory, which basically applies some features to the data, which could also be like differentiation, so that the actual features are more stationary. And the important part within this block is that it's causal, because we want to predict given past, not have a leak within the architecture, so that the model sort of optimizes for just finding the path to connect to the proper sample, so that we disallow leakage of the information. So given calculating those features, we perform this abstraction with limiter operations. So basically, we have those two twin tensors removed from each other and limit the values, so that the outliers that we assume that are present within the data are limited in sort of the information about the value that the outlier is present. However, it doesn't impact the training as much, so that we limit the impact of those on the gradient, so that the learning is actually possible. With this layer also comes the important part regarding the loss function, which I will talk in the following slide. When we have this, also, actually, why I do this subtraction. So basically, we want to have the vector that is nicely distributed in a way that is, we could say that is somewhat normally distributed around 0 and 1, parameters 0 and 1. However, without assuming the normal distribution. So that's why I said describe it as a nicely distributed, because I don't want to assume the normal distribution within the features as I assume the SGC distribution. So I cannot do that. So that's the part that I have embedded within the loss function. So this nicely distributed component is important, is crucial for the LSTM network because it is prone to gradient explosion, vanishing gradients. So the input actually has to be nice. It has to be within given range so that the sigmoidal function doesn't saturate and we are within the range that that we can efficiently perform the optimization of the neural network. So this is pretty much the extension of the block that that was already introduced, the causal CNN block, however, with the addition of the LSTM layer, so that we have both the extraction of the features while treating the temporal aspects of the data. And so we are not only considering like very local aspects, however, we can also go back to the past within the time series. With this, we also incorporate the proposed GLU6 activation function, so that it's basically an extension of the very well known GLU function, which is just basically the x times the PDF of the CDF of the normal distribution. So this is very similar to the operation that we perform on the subtraction with limiter layer. So again, the impact of the outliers is limited. So the last part is that we split the obtained embedding tensor to 6 tensors and move it through the multi-layer perceptron block. So this is very simple block with just 3 linear blocks followed by GLU activation function. It is basically to allow prediction of all of the parameters for the distribution and also the outlier task that I will talk in the following slides. So basically, throughout the whole architecture, we fix the length of the trajectory so that we have this ability to sort of predict, given the vector from 1 to t plus tau, to predict the 2 times from 2 to t plus tau plus 1. So that's we are holding on to this t dimension. Okay, so how do we optimize this neural network? So basically, we need to define the loss function. So first component is, as I said, it is very important that we use the distribution with the PDF defined. So we use the negative log likelihood loss function. So basically, for each time step, we minimize the logarithm of the PDF. Another part is the part regarding the element that was in the subtraction with limiter block. So we optimize it for the values to be surrounded around -1, so that the overall average expected value will be around 0. However, there will be spread around -1, so sort of the standard deviation will be 1, without actually stating that this is like normal distribution, which I highlighted in the previous slide. The outlier task that I will talk about in the next slide is just the cross entropy within the classes, and the last component is the L1 regularization on the weights, so that especially the early features, the early CNN layers, don't fit to the very high values of the trajectories, because we some highly non-stationary data, exponentially behaving data. So we don't want to very high values of within those features, because that would just say that we actually didn't learn patterns within the data. We just learned to sort of digest the exponential function. So this auxiliary task is basically just a supplemental task that allows more efficient, maybe more enhanced training of the neural network. So this is a task that we don't really care with our main purpose. We just add it because we have the data and we can actually use it to better inform the model. So within our task, it is basically the distinction between those three states that Professor Wyłomańska has said, that we have the pretty much constant state where the machine is healthy. We have linear state where the with the degradation component state is, and the critical where the exponential one is. Of course, like it is simplification. It's not clearly like constant, linear, and exponential. It is like somewhat this behavior. So moving on to the comparison of the models and actually evaluating the models, and also to the plots that Professor Wyłomańska has showed you on her presentation. We see that the Gaussian-based model, so basically the model without any features, any novelties within the model that we proposed, that I enumerated throughout the presentation, and with the Gaussian distribution embedded within the network. So instead of the SGT distribution, how it performs, so we can see that pretty much the response to any outliers is like catastrophic to the prediction. So we see that for the orange parts, so this one-step prediction, and the red parts is the like full forecast. So it's unknown. So pretty much this whole vector is provided to the neural network. So within this embedded for this tensor that I showed you on the very previous slides, those are the values of the trajectories, and for reds, those are the zeros. So yeah, so we see like very high response. The model isn't capable of returning to the actual value of the distribution. So it's like very disruptive for this trajectory where the outliers are less prominent. We see that model was able to come back. However, like as we see, the outliers were contributed to the potential scale of the model. So the uncertainty of them happening again is very high. Whereas for our proposed model, like the response for those peaks is negligible. Like there is no actual response for the like quantile, because those are quantile lines. So the outliers are of less impact there. And we see that pretty much the distribution follows the data tightly. So, however, I just showed you two trajectories, so I could just cherry pick those. So moving on to the evaluation, I used the Kolmogorov-Smirnov statistic. So basically, like here is the Kolmogorov-Smirnov statistic. However, I have like multiple samples for trajectory. So I averaged those statistics through the whole length of the trajectory, of the predicted trajectory. So we see that, for the evaluation, I use two distributions. One is within the family of the SGT distribution, and the other one, alpha stable, that is not. However, it is like also heavy-tailed, and also we see that it's very commonly in the data. So we wanted to evaluate how the out-of-distribution data would impact the performance of the model. So we see that the Gaussian-based model, like for the degrees of freedom where the data is actually very close to Gaussian, like it behaves very similarly. However, as the number of outliers increases, like the degradation is severe, and the predicted distribution is pretty much don't match the true distribution at all. For alpha stable distribution is very similar. We see that the model based on SGT doesn't degrade that much. However, Gaussian based degrades severely. So used the simulator that was proposed within the Wojciech Żuławiński et al. Publication. So this simulator also is used for simulating data that is those buff curve health index data. So we see that overall, like the error has increased. Like this is slightly above 0.1 for the SGT distribution. However, it's still very small, and the degradation with the increasing number of outliers is still very present within the Gaussian-based model. So now I'm moving on to the actual real data, because like we want to apply this method in real case scenario. So the upper plot shows the one-step prediction on whole trajectory, and the lower part the one-step prediction, and followed by the whole unknown prediction for the 256 samples. So we see that the distribution could be captured, was successfully captured through even like very small scale time series to like, exponentially behaving trajectory. Like the model could follow this actual behavior. And for the forecast, we see that maybe it like didn't capture like these very high values. However, within the given probability, it was able to actually predict that it could happen. So the lower bound here, it contains this part. However, it captures the possibility for the machine to actually go broken, because this trajectory ends here. So basically, at this point, machine was broken and didn't work at all. Okay, so another example, the wind turbine data set. Here we see that the bathtub curve is not much, maybe isn't as visible as in the previous example. We see so much more wiggliness to the data. So again, this is like comparison from the simulation and how the actual real data looks like. And here we see that like overall, the one-step prediction follows the data quite tightly, even very major disturbances within the how the data behaves. And yeah, so here the example shows that pretty much model was pretty much confident that the machine would go broken. However, like it still captured the possibility for it not going into the like with so lower probability to be still maintaining within some healthy region. So we can see that pretty much for the last few samples, the behavior was highly increasing. Like it was indicating that pretty much the machine could be going to the state of being absolutely broken. So yeah, so this actually could shed some light on some warnings within the like industry. Another example, the last example from the IMS dataset. So we see again, like the increments within the data are much more like the behavior is more jumpy. So we see that, like for example, here with the steady, then sudden jump, steady jump, jump. So we can see actually, because it is one-step prediction, that the prediction captures this behavior. So the one-step prediction is predicting that it is possible for the sudden jump. So so that's why we see the enlarged upper quantile, which also allows us to capture this possible very high jump that also happened where the machine like got broken. Okay, so the conclusions. So based on all of the evaluation on simulated data, real data, we have shown that the model is capable of actually really forecasting the distribution of the data that could be used for the rule, so remaining useful life prediction. And with the comparison to the Gaussian model, it has been shown that the nonlinearities that were proposed actually work and are significant for the performance of the model. The proposed embedding, the proposed input vector actually allows us to efficiently perform the long-term prediction. And within this architecture, we use the features that actually allows us to train the model in a like feasible, stable way that because like the LSTM neural networks usually are hard to optimize because of the vanishing gradient problems or exploding ones. So all of the parts within the neural networks highly mitigate those issues. So thank you very much for your attention. The work was supported by the project that Professor Gumeńska already has said. And yeah, it is based on the paper that is available under this.